Anyway, he's from Lisbon, and well, you know the title. And in this case, the answer to the question is probably maybe. Anyway, Pedro.
Well, you stole my lightning already, because that's exactly what I was going to say, to give the answer straight away. The answer is maybe. More accurately, the answer is I have no idea. Well, some idea. Anyway, a pleasure to be in Davis for the first time, and thanks very much to Jack for the invitation. And I apologize in advance for the havoc that my talk is going to cause on your digestions, but, you know, not really my fault. As for the institutions, it's very simple. This one is the most important one, because this is the one that pays my salary. Everything else is just research. Right, so this is work I've done with Absalom Arif and Luis Santos, accepted 2 days ago for JHAP, for which we are extremely happy, and work for which, in fact, Jack, Sabine, and Jan had quite a deal of input, which we very much appreciate. Anyway, the LHC has discovered a new particle. We know already that it is a scalar with a mass of about 125 GeV. By the way, it has to be 125, it cannot be 126, because 125 is 5 to the cubed. There is no better answer for that. It has to be 125. Up until now, everything about this particle is compatible with what one would expect from the standard model Higgs boson, which is all fine and good, but it's also extremely boring. So what I'm going to talk about in this lecture, in this seminar, is what one can achieve in the Two Higgs Doublet Model concerning these data. This model was proposed by T.D. Lee in 1973. It's one of the simplest extensions of the standard model. It has a great deal of interest in many different ways. For instance, certain versions of the model have dark matter candidates. It has a richer scalar sector, and the reason why T.D. Lee introduced it, it can actually have spontaneous CP breaking, and so presumably help to explain the matter-antimatter asymmetry in the universe. So if you want to know more about the Two Higgs Doublet Model, you pester Jack Gunnion, here present, who will tell you a lot more about it. Or you go and read this physics reports that some guys wrote.
Well, a little bit after Lee's paper, a few years, wasn't it Glashow who categorized type 1, type 2, etc.?
Which will come.
You're going to come to that.
Yes. So, for these models, you could argue that they are the simplest standard model extension, but this is personal prejudice. I don't quite like H singlets. And we have, surprise, surprise, two Higgs doublets, phi 1 and phi 2, instead of just the one. The wonderful thing about this model is that, for starters, it doesn't screw up anything that the standard model does well. Okay? This is a model that, as I'm going to say, can be reduced to the standard model in certain limits. And as an added bonus, the Two Higgs Doublet Model is a simplified version, or at least a mimic, of one of the sectors of the supersymmetric ones. So they are embedded, included in more general ones. And as I said, and this is very, very interesting, it doesn't seem to quite work, you could have spontaneous breaking of CP in these models. I'm not going to talk about CP breaking vacua here. All the minima that I have here are just minima which preserve CP. So the two Higgs doublet potential, if you have two doublets, then your very simple Higgs scalar potential in the standard model, which only has two parameters, suddenly becomes far more complicated. You have three quadratic terms, M11, M22, and M12, and then you have seven quartic couplings. Some of these can be complex, so in fact, seemingly, you have 14 independent real parameters. In fact, they're not 14, they're just 11 due to rephasing invariance. Still, quite a lot, quite a huge parameter space. Now, this is the most general one, but the one that people mostly study isn't this one. It's the model that Glashow, Weinberg, and Pashos separately introduced in 77, if I'm not mistaken, in which we introduce a Z2 symmetry in this potential. Namely, we flip the sign of the second doublet phi 2, which immediately makes this guy go to 0. You'll notice that it's phi 1, phi 1, phi 1, phi 2, so that goes to 0. Lambda 7 also goes to 0. And this other term here, this quadratic term, would also go to 0. Usually, though, one leaves this guy there, a real M12 square, to softly break this Z2 symmetry. And the reason why this symmetry was introduced was not just to curtail the number of free parameters in the theory, was in fact to avoid Higgs-mediated tree-level flavor-changing neutral currents. That's an mouthful. Because with this Z2 symmetry, those FCNC currents mediated by the Higgs, which occur in this model, do not then occur. Right. So the softly broken Z2 potential has... Was that a question? Sorry. Has 8 real independent parameters. That guy, well, all of the couplings are taken to be real here, so we put an extra CP symmetry on top of it. And we have to extend the symmetry to the whole Lagrangian, otherwise the model would not be renormalizable. And the way you do this, well, you can do it in several different ways. The two most used in the literature, more or less, are model type 1 and model type 2. In model type 1, only one of the doublets couples to the fermions, per tradition phi 2. Model type 2 is the analogous of SUSY. Phi 2 couples to the up quarks, phi 1 couples to down quarks and leptons. And then there are several different other possibilities concerning the couplings to the leptons, but these are the only two ones I'm going to talk about. Again, with this symmetry extended to the fermion sector, you are ensured that no tree-level flavor-changing neutral currents occur. And as I said, okay, if one Higgs doublet pisses a lot of people, two Higgs doublets will piss a lot more. There is much more in the scalar sector of the 2HDM than in the scalar sector of the standard model. In the standard model, you just have one single individual boring scalar. Here you have 5. You have two CP-even scalars, little h and big H. And we are going to assume that that guy there is the one that was discovered. It's the lightest of the pack. This is the 125 GeV state. And then you have a CP odd scalar, i.e. a pseudoscalar, and you also have a pair of charged scalars. How do you distinguish between these two guys? They're all neutral. Well, they decay to a lot of things, just like in the standard model. Both little h and big H decay to 2 photons, ZZ, WW, but they decay to 2 fermions. And in fact, and you're going to hear a lot about this, the heaviest of the scalars, if it is sufficiently heavy, not necessarily that, because you can have off-shell decays, but if it is sufficiently heavy, can decay to a pair of the lightest scalars.
So
whereas
these statements are true either for type 1 or type 2?
Yes, yes. But the decays don't occur exactly in the same way for type 1 and type 2.
Right.
For instance, here, in the decays to the fermions, the couplings are slightly different. And there are some things you could do with one of the models, type 1, or another one. So for the pseudoscalar, well, the pseudoscalar also decays to 2 fermions, also decays to 2 photons. It will not decay at tree level to ZZ or WW, being a pseudoscalar. And there is an extra decay, which I haven't shown here, but I'm going to talk about in a short while, which is that if this guy is sufficiently heavy, it can actually decay to a Z and an H. So it can actually have a decay with a scalar in the final state. Right, and as I said, certain versions of this model, for that you would need to exclude the soft breaking term to leave the symmetry intact, even intact by the vacuum. Certain versions of this model provide you with very good candidates for dark matter. We call them the inert model. And as I said, it's based on the unbroken discrete symmetry Z2. This was introduced in '78 by the Spande and Ma, and got a lot of attention recently due to the work of these people. Right, so this horrible thing that's here with these 8 parameters, okay, it's less horrible than the most general 2 Higgs doublet model potential, But you're not at liberty to consider whatever values you want for these couplings. You are not at liberty in the standard model to grab the scalar potential and consider whatever values you wanted for the two couplings there. For starters, the potential had to be positive at infinity. If the Higgs scalar, if the Higgs field was tending to infinity, then the potential had to be positive, which meant that already in the standard model, the quartic coupling needed to be positive. Here is the same thing. You have more field directions, depending on these two doublets. If either of these guys is tending to infinity, then you need to make sure that this potential is bounded from below, that there is no direction along field space along which the potential can tend to minus infinity. The reason for that is you need the existence of a stable minimum. So this puts some constraints on the quartic couplings of the potential. Lambda 1 and lambda 2, for instance, need to be strictly positive. Lambda 3, 4, and 5 could be negative, but they can't be too negative. And these are necessary and sufficient conditions for the potential to be bounded from below. And again, just like in the standard model, you want to impose that your theory obeys unitarity, that it respects unitarity. And again, you calculate a handful of amplitudes, which depend on the quartic couplings, again on the quartic couplings. And if you demand that in modulus they're all smaller than, in this case, 8 pi, then you're guaranteed that the theory respects unitarity. So these are theoretical bounds on this potential that have to be obeyed so that the theory makes sense. Then, of course, yes.
So when the potential is bounded from below, in standard model, when you put reduced fractions, it's not bounded from below, right? So what do you do here?
This is tree-level. These are tree-level conditions, which can be improved if you do the same thing as in the standard model, in which you do an RG running and you impose that they are valid on all scales. If you do that, then the available parameter space of the model gets even more constrained. Okay, I'm not doing that here. I'm allowing these guys. I'm just imposing these conditions at the electroweak scale. But yes, you could do that.
But it's possible to find local minima even if you violate this at the tree level.
It's possible to find local minima. Yes, it is. Indeed, it is. I just wouldn't feel very comfortable working in a theory like that. But yes, it is possible. Right. Okay. Though so much for theory bounds, what about the experimental bounds? Even before the discovery of the Higgs boson, we already knew that there were some things which were constraining the theory immensely. Namely, there was a wealth of precision electroweak data, which, if you impose it via the ST and U parameters, impose severe constraints on the parameters of the potential. One of the possibilities, for instance, it's not a single one, to obey these constraints is to impose that the charge scalar and the pseudoscalar are nearly degenerate in mass. But that's not mandatory. There are other ways of escaping them, of escaping these bounds. Okay, so we had to take that into account. And also, the fact that you have a charge scalar in the theory gives potentially large contribution to the physics phenomena. And in fact, some of the most stringent constraints on these models come from the physics analysis, namely B to S gamma, Z to B bar constraints, and a couple of others. They are different from model to model due to the different couplings of the charge scalar to the fermions. Roughly, you could say that these constraints from the physics impose that tan beta, which is the ratio of the VEVs of the two doublets, has to be larger than 1. And for instance, for model type 2, not only that, but the charge scalar has to have a mass larger than, and then it depends exactly on which paper you quote, let's say larger than 360 GeV. Of course, there have been direct searches for scalars, for charge scalars in particular. There is a lab bound of about 90 GeV, which also has to be taken into account. And of course, Atlas and CMS themselves, they have found one scalar, and they have put plenty of bounds on other available scalars, some of which I'm going to talk now
Sorry, for the
Yes.
for mu to E gamma, for example, even the neutral scalars, like a heavy neutral scalars, can also give you this loop contribution.
mu to E gamma.
Oh, sorry, B2S gamma. Sorry, I just said the same thing.
Wouldn't you need to have flavor changing neutral currents for that?
So for the heavier scalar, or you say if the Yukawa coupling is aligned, then there's no...
If there is FCNC, definitely, there is a contribution there. If there isn't FCNC, I don't think the neutral scalars would contribute. But I may be wrong, okay? That, off the top of my head, that's what I would say. Right. And we're going to assume, as I already said, that what we have seen is the lightest CP even scalar, little h. It's not mandatory for this to occur. Apparently, there is still some corners of parameter space in which you could say that what we have observed is actually the heaviest CP even scalar. But then, okay, it's very difficult. You then have to explain why you hadn't observed the lightest one. So
the word on the street, though, is that that's not possible because of the bounds on charged states.
Which wouldn't surprise me at all. As I said.
So we're kind of discounting it now in CMS anyway. The idea that what we've discovered is the heavy scalar, CP even scalar.
Based on the charge Higgs, good to know. Right.
In the MSSM,
Pardon me?
what context is this?
Yes, in the context of the type 2 Two Higgs doublet model. I think it doesn't matter if it's MSSM or not, unless they're competing.
But the charged Higgs and the capital H mass are independent quantities in the general Two Higgs doublet model.
You don't have the same mass relationship?
No.
MA10 beta?
No.
What about the T problem constant?
Well, I mean, we're doing scans. Jan and I at the moment, we have lots of solutions where the capital H is at 125 and it obeys all the constraints that Pedro was talking about. So I think the answer is it's allowed.
There's always the possibility of invisible decays.
Yes, in any of these models, there's some room for that at the moment.
But if it's just a type 2 Two Higgs doublet model without any SUSY particles, have we ruled that out or not? I don't think so.
No.
I wouldn't think so.
Okay.
Okay. Right. So what have we done? We have an 8-dimensional parameter space. Okay, 2 of those parameters have to be fixed because we know the W mass and now we know the Higgs mass, but still you're left with a 6-dimensional parameter space. So what we try to do is to make as general a scan as possible, such that the Higgs mass is 125 GeV, the W mass is 80 GeV, all of the masses are taken to be above 90 GeV. This is just a general thing. Of course, the capital H mass is taken to be above 125 GeV and below, say, 800 GeV. You could take it even further, but for our purposes, this was enough. And 10 beta between 1 and 30, and the soft breaking parameter also with a wide region of variation. Then we ensure that all of the theoretical constraints I mentioned are obeyed, and all the current experimental bounds are also satisfied. We then calculate all of the branching ratios and production cross-sections at the LHC, and we compare with ATLAS and CMS. And as a result, we discover something very, very comforting, namely that the 2HDM can fit the current LHC data at least as well as the standard model, which is fine and good, because if it wasn't so, then this would be a complete waste of time instead of just a relative waste of time. Right, so this, though, isn't completely surprising. In fact, the Two Higgs Doublet Model is a theory that has a decoupling limit. Essentially, if you take the extrascalars and take their masses to infinity and do some fine-tuning, some tuning in the angles, then this theory reduces, more or less, to the standard model. So it's good, of course, that we're recovering the standard model limits values, but it isn't entirely surprising. Of course, what's interesting is what are the differences between these two things. So just a quick reminder that currently most of the observables we compare to data are ratios, sometimes called mu ratios, we're sticking with R, in which what you're comparing is the ratio of what you have measured against what you would expect if the standard model was correct. Namely, these ratios are production cross-sections times branching ratios, the production cross-section of a Higgs in a PP collision, and its decay to some final state. 2 photons, ZZ, whatever. And what I'm going to show you are data in which what's above is not necessarily what was observed, but what one would expect from the Two Higgs Doublet model. There are differences in the production side and also on the decay side, which can account for some deviations. And there are plenty of different processes of the Higgs at the LHC. The dominant one is the gluon-gluon fusion. There's also the VBF processes, BB bar fusion as well. All of those we took into account. Right, so what about the heavier scalars? What about the heaviest CP even scalar, capital F, and the pseudoscalar A? Our experimental colleagues have provided us with exclusion plots, which I'm going to show in a short while, in which they, made a scan, so to speak, along the mass of a hypothetical scalar between, say, 100 and 1,000 GeV, and again, what we plot is a ratio. It's a ratio what has been observed versus what was to be expected. Namely, what was to be expected for the production of a standard model-like scalar with a mass identical to MH or to the pseudoscalar A. And the ratios RH and RA that I'm going to show you correspond to these ratios here. So the question is, so far, neither Atlas nor CMS, as far as I know, have discovered anything else other than the 125 GeV state. So how much parameter space of the Two Higgs Doublet model can we already exclude based on the fact that no extra scalars have been observed? And this is the type of graphs that the experimental collaborations give us. And here, for instance, you see the ZZ exclusion data, in which this black line essentially tells you that everything that's below this line is still allowed, everything that's above that line has to be excluded. The same thing here for the WW scan. The 2 photon mass scan ends a lot earlier, 150 GeV. According to my experimental colleagues in Lisbon, this is a hellishly difficult thing to prolong above 150 GeV, which explains why there aren't that many data after that. And also the tau-tau exclusion data with mass. Right, so for the WW then, we grab all of our data concerning the decays in production of the heaviest CP even scalar, and we have loads and loads of points. Each of these points corresponds to a different selection of parameters in the Two Higgs Doublet model, and we compute this ratio I've showed you to WW and see, okay, what does this look like? And what it does look like is that there's plenty of points already above this exclusion limit which have to be excluded. If, for instance, that guy there, that combination of parameters, that there would tell you that you would already have, in principle, have seen an extra scalar with a mass around 300 GeV decaying to WW, but you haven't. So only the allowed points, only the points below this line are allowed. And there's plenty of combinations of parameters which are already excluded. And the same thing for the ZZ case, both in type 1 and in type 2. Again, everything above this line is excluded, everything below this line is still allowed. So you have here a glass half full, glass half empty situation. Glass half empty, you're excluding a lot of points. glass half full, you still have plenty, really plenty of different combinations of parameters which are still allowed. So the non-observation of a heavier CP even state decaying to ZZ or WW isn't, up until now of course, enough to exclude this model. And in fact, within the Two Higgs Doublet model, this isn't entirely surprising. Why? Well, because you have a sum rule concerning the couplings of the two CP even states to the gauge bosons. Essentially, this coupling here, G, from the lightest CP even state, is sine beta minus alpha, and this guy is cos beta minus alpha. And of course, sine square plus cos square have to be equal to 1. So what is LHC telling us? LHC is telling us that this guy, little h, is behaving essentially just like the standard model. So this coupling here is very close to 1, which means that this coupling here has to be very small, very close to 0. Namely, if this guy likes to couple to gauge bosons, then this guy won't like to couple to gauge bosons. And in fact, there are plenty of parameter choices for which we see that it's not coupling very strongly to gauge bosons. And so everything is pretty much making sense, so to speak. There is a technical detail concerning these plots, which was pointed out to us by Fabio Maroni, which is the possibility that for large masses of the CP even state, the width of this particle could actually increase a little, and then you'd have to start worrying whether or not you might have an interference between H decaying to ZZ, for instance, and the ZZ background. Okay, that's a small contribution. The studies that have been done along these lines have shown that at most you'd have a 10% effect. We just decided to be conservative, and instead of taking this line, for instance, we took it 10% above. So we just were conservative that way. It doesn't make that much of a difference.
Of course, with the little h standard model like capital H, does not have to be width, right? Because the big width mainly comes from WW and ZZ. So in fact, capital H, given the constraints, especially in type 2, is pretty narrow, below 5 GeV.
That's a good explanation as to why we haven't found big widths, actually. We decided to take this just to be on the safe side, but we were sort of surprised that the width wasn't monstrous. But yes, you're right. That's a very good reason. Thank you. Right, so this for WW and ZZ. For the tau-tau, things could become interesting. Not so much for the heavier CP even state. The heavier CP even state isn't decaying to tau-tau or BB, by the way, very much. So all of the points we generated for type 1 and for type 2 are well below that line. But for the pseudoscalar, the situation changes. The pseudoscalar can actually decay a lot to tau-tau and BB, so there's quite a lot of parameter space here that you can exclude based on this non-observation in tau-tau. And in effect, we know that the tau-tau data is still, in the beginning, so one would expect this line to come down as soon as more data is taken, and that's going to be very, very interesting. Especially in type 2, the decays and production of the pseudoscalar are enhanced for large values of 10 beta, so you can have a lot of points here. So this is something that we should look very carefully in the future at the tau-tau exclusion plots coming from LHC, because I think that they can be very, very useful. Right, so as for the photon-photon, okay, I decided to show you these plots, which are seemingly, well, they are horrendous, but they are seemingly useless, but just to show you that, okay, our experimental colleagues, for very good technical reasons, because as I said again, this is very difficult to do, they only provide us with an exclusion bound up until, say, 150 GeV. So that line that in the previous plots goes to 600 or whatever, here ends there. And so we can't say anything about what's being excluded to the right of 150 GeV. You can only say, okay, the only things allowed are those that are below this line up until 150. From here on, everything is allowed. But this shows you that if, and I believe this is being worked on at the moment, if this exclusion can be extended to larger masses, again, due to the pseudoscalar, there is the possibility of excluding a lot of values of parameters. Because this rate to gamma gamma can be enhanced to very high values. You'll notice that here, this is 10 to the cubed. So the pseudoscalar can decay for certain masses, and that sharp drop there is just the TT channel, the TT decay of the A that suddenly comes into play. The gamma-gamma rate of the pseudoscalar can actually be very high, a lot higher, hundreds of times, if not even 1,000 times, than what you would expect for a standard model like scalar. This, of course, isn't saying much, okay? This enhancement of hundreds or even thousands is perhaps not very significant because, you know, perhaps you have sigma times branching ratio that's gigantic compared to what one would expect in the standard model. But our experimental colleagues essentially think in terms of number of events. So say that this cross-section times branching ratio is enormous compared to the standard model, but that would correspond to observation of a single event. So this,
we
yes.
Searched for high-energy diphoton resonances, high-mass diphoton resonances, and we didn't use Higgs as the signal model, but you know, other things.
Where is that data? Because I couldn't find it.
Really, I'll have my laptop, but I think we could adapt the cross-section times branching ratio limits from those
Okay.
to this.
That
I don't know if we go all the way down to 200 because the trigger, the diphoton trigger, was maybe not low enough threshold for that.
I would love to see that because, you know, this is ridiculous. I mean, 1,000?
No, that would certainly not. And this would be a resonance too. That's pretty fairly sharp.
Yeah,
I mean,
right.
Yes. I would love to see that.
All right.
Right. Okay. So this is really just to show you that if indeed there is more data for higher values of the mass, then you know we could kill a sizable chunk of parameter space here.
The other comment, of course,
Yes.
is that at least the direct or irreducible gamma-gamma background goes down very rapidly at these high masses, so the signal would be quite clean unless there's some irreducible background that somehow creeps in.
It's becoming sweeter than
We have a fake background, but it's,
Well, that's what I'm talking about. Yeah.
it doesn't peak. So.
Right.
Okay, so if you combine all of these exclusions, the non-observation of an extrascalar in WW, ZZ, tau tau, and gamma gamma, then you cut a lot of parameter space. But to be honest, yeah, we have plenty of parameter space available, and these exclusions, though important, are not eliminating, you know, any interesting regions. So there is a lot of parameter space already excluded, but there's still a lot of points remaining. So the model is way distant from having been excluded. So there is another possibility, which is the following. Okay, we haven't observed anything decaying to WW, to ZZ, to tau tau, or anything with higher masses. So what if, indeed, these guys, capital H and the pseudoscalar, are not decaying to WW, ZZ, to the usual decay channels? Because indeed, they can decay, H can decay to two little h's, and the pseudoscalar can decay to ZH, amongst other possible decays also involving scalars. And if you look at this, this is just in terms of the heavier CP even mass, the branching ratio of H to two H's. And you see that, you know, for quite a number of possible parameter choices, this branching ratio is very close to 1. And the similar thing for the pseudoscalar. For a wide region of parameter space, the A can be decaying mostly to ZH. So big deal that you're not observing it in tau tau, it's mostly decaying to something else. And if we take the extreme notion that in fact this was exactly 100%, so this guy would be invisible in every other channel, the only way that you could hypothetically then infer its presence is by studying the two H's. By studying the Higgs that you have already seen, you would get information from the heavier state. Likewise here, if this decay were occurring with 100% probability, then the only way to infer the presence of the pseudoscalar would be to study this decay. Now this decay can occur, has an off-shell component that you see here and also here. If not, it would start at 250 GeV, say, and there at 216. So there is an off-shell part here. It's actually, for what I'm going to show, it's there. It has been taken into account. But most of the contributions will come from the on-shell bit.
So, two questions.
Yes.
What's the line at 700?
That's just because my simulation ended mostly
That's
there.
right.
Actually, no, sorry, no. It's an artifact of the simulation. It isn't really, but essentially, forget what's beyond 700.
The more important question is, if the branching ratio of either one here is large, near 1, aren't the production cross-sections also affected in some way then? Because you have to be, I don't know if they have to be, but
this decay here
we're
depends on...
relying on the gluon fusion.
Right,
Yes.
so it's only the
It's
top
mostly
and bottom
gluon fusion.
Yeah.
So that's the fermionic coupling, what?
Yeah, so it's just entirely determined by fermionic
So,
couplings, yeah.
so I guess what I'm asking is the fermionic coupling staying constant while this bosonic coupling is just getting large, or is there some sort of seesaw?
Well, the main decays of the capital H are, well, it depends what mass you are, but if you're below top anti-top threshold, then there are the usual things, B's and taus, and so this HH is competing with various small coupling constant decays, right? So unless you suppress this HH coupling constant to the capital H, then this will automatically take over.
But I can imagine,
But for instance, the production of a pseudoscalar via gluon fusion is by itself, the cross-section tends to be larger than that of a scalar of the same mass. It's just because the triangle is different.
yeah.
And for type 2, if I'm not mistaken, it's actually enhanced with 10 beta, it grows to 10 beta, the bottom coupling contribution, or for low values of 10 beta, you'd have a strong top contribution here. So to answer your question, you can have this large while keeping the production cross-section also observable.
Okay.
But of course, you could then also have exactly the other way around because you have a lot of wiggle room. But definitely, what I'm going to show you are the rates, the contribution to the rates, and you see that you can have both things large. Okay, so this would mean that crazy idea time, there is a possibility. Yes?
Just a quick question about the comparing the two plots. Are they independent parameters that are affecting them? Essentially, if you have some point on the top, it's good for the H to HH.
You're asking if this can occur simultaneously?
Yes.
Almost certainly, yes. For instance, this coupling here is essentially sine or cosine, we don't have it by heart, of beta minus alpha. So two angles. Here you also have beta and alpha, but you have a contribution which depends on the soft breaking term. Okay? So it's a separate parameter that you can put in there. Okay? So almost certainly yes, but to be honest, I would have to check. I would have to grab this code and check if this is large, whether that can be simultaneously equal. In principle, I would say there's nothing preventing them to be equal. Okay? Okay, so there is a possibility that actually some of the Higgses that we are watching at LHC are coming not just from the direct production via gluon, VBF, BB-bar fusion, or whatever, but also from this chain Higgs production, in which first you produce say the big H, or the pseudoscalar, or the charge scalar, and then those heavier scalars decay to the 125 GeV state. So all of the rates that we compute then ought to have, in a very naive manner, and I'm going to criticize this towards the end, but for the moment, take it as is, all the rates should be the total rates, computing the direct cross-section and also the chain cross-section. And the chain rate is just the production first of a capital H and then its decay, or a pseudoscalar, or the heavier charged one. Right, so these guys are chain H, for instance. What are they? Again, they are ratios, and what's in the denominator is what was expected for the 125 GeV state in the standard model. Its production cross-section in the standard model, and the branching ratio of its decay to a final state. And what's in the numerator, though, is something different. It's the production cross-section within the Two Higgs Doublet Model of the of the heaviest CP even state, capital H. You'd have the branching ratio decay of little h to f, and then you have something in the middle, which is essentially, if you produce capital H, how many little h's do you get in average, so to speak? So it's kind of the expectation value of h's produced in capital H decays. Sometimes you can get 2 little h's, sometimes you can get 1 little h, and these p's, capital P's, are just the relative probabilities. And now I'm going to show you incredibly complex formulas, hoping to stun you into submission. There were quite a few typos in these formulae, which, thanks to the help of Davis, we were able to hammer out. But one of the possibilities say that probability for you to get 2 h's has a dominant contribution. Okay, it's dominant. It's the branching ratio of capital H to 2 h's. But there are other possibilities. You could have capital H, if the masses are correct, first decaying to H plus, H minus, and then H plus decaying to W plus H, and H minus decaying to W minus H. And so you have that square there. And plenty of others, such H decaying to AA, and then both A's decaying to ZH. So plenty of others. Please notice that, in fact, as I said, that's the most important contribution, okay? But, you know, given that our code has all of these branching ratios inside, might as well take everything and try to be coherent. In most cases, these decays are kinematically forbidden because the initial particle is not heavy enough. And also, you could have the capital H decaying to a single Higgs. For instance, H decaying to ZH, and then A decaying to Z little h, and several others. Likewise, you would define a similar thing for the rate of chain production involving a pseudoscalar. And the pseudoscalar can also have a couple of decays in which it produces 2 little h's, but mostly decays to a single one, that decay A to ZH that I've just showed you. So, all of these horrible formulae are then put into our scans, and then one has to ask, okay, does this make a difference? I mean, you're having all of this hard work. Does this make any impact on what you could observe for the decays of the 125 GeV state? And the answer is, fortunately, yes. It can have an impact. There is an underlying question behind these plots, which I will address before the end. But for the moment, let's just look at the observed rates, the rates we are seeing for gamma gamma or ZZ coming from the 125 GeV scale. Now, this is type 1, and in type 1, you do an analytical calculation and you show that the rate to ZZ, the direct rate to ZZ, has to be smaller than 1 or at most about 1. No such restriction for the gamma gamma. So in this plot, what I'm showing you is I grab all of my points, all of the scans that I did of the parameter space. I pass through all the experimental constraints, including the non-observation of heavier scalars that I have spoken. And in blue, you have all the contributions coming only from the direct production. So this is what one usually computes. With green, I include both the direct production and the chain production, so the indirect production. And you see something interesting happening, which is that, you know, you could actually have an enhancement on ZZ that you can't if you only consider the direct production mechanisms. You could enhance ZZ whilst keeping gamma gamma close to 1, for instance. You could also enhance slightly gamma gamma. So for instance, if if you look at the data currently, Atlas and CMS is giving us intervals for these rates which are on opposite sides of 1. CMS is seeing constantly less than 1, Atlas is seeing constantly above 1. To 2 sigma, if I'm not mistaken, the results are of course compatible. But if Atlas is right, for instance, and you have ZZ larger than 1, this would be a possibility within model 1 of accommodating those data. For model type 2, the rate for ZZ and for photon-photon isn't as constrained as is here. It can assume absurd values. What we are observing, of course, is that these rates seem to be concentrated around 1. So the question, so the comforting thought is that chain production along with direct production can yield also perfectly reasonable values of the observed rates. So the question is, how important can this be? We've seen that it can have an impact on the chain production, on the observable rates, but of course the rates that I showed you in the previous plots go all the way from 0 to 1 or whatever, and we know that the current experimental bounds are concentrated in a rectangle somewhere here around 1, 1. So, with these two plots, what I'm showing you is, in the vertical, it's the ratio of the number of Higgses produced via chain production divided by the total number of Higgs produced, both chain and direct production. In green, you have everything, all the points possible, all the points imaginary. In blue, you see what remains after I make a cut and say, listen, let's assume further that all the rates observed at LHC for ZZ, for WW, tau tau, photon photon, are within 20%, yes, 20% of the standard model expectation. And you immediately see that this goes down to about, at most, 25%. So again, glass half full, glass half empty situation. The glass half full situation is that you can assume that within the Two Higgs Doublet model, at most 25% of the number of Higgses that you are observing now could be coming from the indirect production from heavier scalars. And so they would be, and this to me is a very cute idea, we could already be observing the heavier scalars without knowing it. Because some of the lightest scalars that are being produced would actually come from the decays of the heavier ones. Okay, so, yes.
Oh, I just want to, so for the heavier MH, like
yes.
the bottom right, is it really just fewer data points there, or is the same thing? I mean, for the left plot.
Here?
Sorry, no, for the larger mass.
Here?
Yeah, for example. Or because it's heavier, then it's easier to see the decay? Or there's really some window that's...
I would expect that, you know, if I left my computer running for another
okay, so you
month,
expect this
would fill up, okay? Because after all the cuts, this is a general scan, you know, grabbing stuff that's not really interesting, but you're trying to cover everything. After all the cuts, you're not left with a huge density of points. I wouldn't look at the density of points here to infer anything.
Okay.
I would really just, you know, take this upper bound here, and that's, to me, what's really relevant. It's the envelope, not so much the density, because, yes...
So still, the heavier the image is you can hide it.
I would think you could occupy that.
Okay.
Right. Before I get to the conclusions, even though I am in the conclusions, there is a problem with this idea. And the problem, and Jack is exploring it at the moment, is the following. Say, yes, that you have 125 GeV scalars being produced in the decay of heavier scalars. Okay, and you observe these plots and say, oh, marvelous, there are contributions to the Higgs rate for gamma gamma or ZZ, fantastic, I'm so happy. Well, there is a problem. The kinematics involved in the direct and indirect processes can be very different, okay? For instance, if these Higgses are coming from the decay of the heavier CP even one, so big H decaying to two little h's, come on, it has to be different for you to obtain two Higgses being produced back-to-back, say, or one Higgs being produced along the beam pipe in terms of the experimental cuts in PT, in pseudo-rapidity and all that, which we haven't done. All this analysis is just cross-sections times branching ratios. The kinematics of the final state have to be different. So there is the possibility that, yes, you could have an extra number of Higgs being produced at the LHC, but they wouldn't be contributing to the current analysis at the LHC because the cuts, you know, they were just decaying to different regions. Okay, so that's one argument. Now the counter-argument, why this is still relevant. I haven't yet mentioned, but in fact, most of the extra chain contributions are not coming from the heavier CP even state. They are coming from the pseudoscalar. Okay, it's the decay A to ZH, and mostly for lower values of 10 beta, and there's a good reason for that, which I can explain later. It's mostly A to ZH, so a single scalar in the final state, a single extra scalar, that's giving these extra contributions. And now, ZH as a final state, that's something that we're already seeing. That's a Higgs associated production with a Z boson. So in fact, there is also the possibility that some of what's occurring in that channel, what's coming from that channel, could come from chain Higgs production. But the most obvious criticism you can do and you should do of this state is you have to do some serious Monte Carlo on these results to see whether or not they would have contributions to what has already been seen. And of course, that's very, very difficult work.
So John,
yes.
let me ask you a question. Suppose we focus on the ZH final state. Well, of course, there's an extra Z there, right? Would you... Oh, he's gone. Yeah.
Trust experimentalists will always escape when you really need them.
I'll have to ask the question another time then.
There was a recent study by Atlas, if I'm not mistaken, about the ZH final state, I mean the ZH production channel, whether you could infer something about the presence of a pseudoscalar there. It seemed a very, basic thing within the context of the MSSM, mostly a rough study, but there's already some work being done on these.
CMS has some results. I don't know if they're public yet or not, but
I would think
it's coming. I think.
I would think it would be very interesting. The least you could do is say, okay, you have this prediction and you have this error bar. So all of this could be living within the error bar, and that's the crudest limit you can put on these things. For me, yeah, that ZH thing is the most important thing, especially because it's most of the contributions that we're finding. So conclusions. Okay, so the LHC hasn't found extra scalars. They're very, very lazy. Come on, it took them 50 years to find a single scalar. You should have already found the other 100,000 that are already there. That's not terrible because this model has such a wide region, such a wide parameter space, that there's still plenty of choices that can give you interesting phenomenology. Namely, the fact that you haven't yet found extra scalars doesn't mean that they all have masses like 100 TeV or anything of the sort. Within the Two Higgs Doublet Model, you can perfectly have scalars above 130. Here I say below 600, but you can have them, of course, even higher. The tau rates in particular, I think, will be very interesting to look at in the next years because they can curtail a lot of the pseudoscalar data or the pseudoscalar expectations. The chain production of the lightest scalars is possible, and it can amount almost up to 25% of the number of total Higgses being produced. And in that sense, and this to me is fascinating, we may already be observing the heavier scalars without even realizing it. Not only that, but if indeed these branching ratios were close to 100%, then the only way of inferring the presence of the pseudoscalar, for instance, would be to look at the lightest scalar. And, of course, plenty of work left to do because this has to be tested. How do we test this? Lots of Monte Carlo needed. And would it really be possible that these exotic production mechanisms would be mimicking the direct production processes? So, it's in red because I really, really don't know the answers to this, and I hope someone can find them. And also, and finally, if you want to know more about this and everything to do with more scalars than just a standard model, please come to Lisbon in September. We have wonderful weather there. We have the sea as well, so you can bathe in the ocean. Because ever since 2009, we've been organizing this workshop on multi-Higgs doublet model. We started in 2009, then 2012. The first poster was blue, the second was red, and obviously we want to form a QCD singlet. So in September, from the 2nd to the 5th, there will be the third workshop, and I hope to see plenty of you there.
Okay, thank you.
Questions?
Any further questions?
Yes.
You're saying that the scene, the associated ZH production, so in these decays, I've been using that as a limit. If they're sensitive to the standard model, is the weight at which you produce HZ significantly higher in those models than it would in the standard model?
It can be higher, it can be lower.
I don't think it can be lower. I mean, there's an electric weak process that's ZH, which is going to be some standard prediction, assuming that little h is standard model like. And then on top of that, you might get these A decays. Yeah.
I just didn't know if there's a big, excess on it that would be...
It depends.
The ZH associated production cross-section within the Two Higgs doublet model is to first order approximation, what you would expect in the standard model, multiplied by sine squared beta minus alpha. I'm saying it by heart, I'm not sure, I'm almost certain. Because this sine squared beta minus alpha is also the coupling of H to ZZ, which you expect, based on the current data, to be very close to 1. The predictions in both models are pretty much the same, although the Two Higgs doublet model, in theory, could be slightly lower. Not too much, but it could be slightly lower. Now, this then would be an extra contribution to that cross-section. Since there's an error bar there, as I said, we could be living within that error bar. And you could put limits on all of this because of that.
For this production, in principle, the A can also be offshore. Of course, here, for like an A to, yeah.
Yes, they can.
Yeah, but here, I guess we assume is you produce A and then decay, and then just look at the branching ratio. Is it? Sorry, I mean
which can be on off shell?
A.
Yes, we took the A to be the possibility of A being off shell in the decay to ZH.
I see.
So yeah, that we took into consideration.
I see.
Even though we accounted for that, mostly the contributions are coming from the on-shell decays, from the region where they occur.
Right. Yes.
But we did consider the off-shell ones.
Because if offshore, the kinematics should be more similar to the offshore Z and Z and H.
You could also have the Z's offshore, yes.
Yeah, I'm just saying that because you are talking about the kinematics can actually be different when you produce this.
Yes.
I'm just trying to think in what limit you are going to have a similar kinematics.
If you find the answer to that, please tell me, because I would really like to know. But yes, you're right, the kinematics will be completely different. I don't know. I think it's a very interesting calculation for someone to do.
Okay, well, let's thank Pedro again.
Thank you very much.